I'm going to be talking a little bit today about what we believe the near future is of airborne geophysics, and maybe a little bit more than just the geophysics part. Now, I know not everything I'm going to tell you today is going to become a reality, but I'm sort of hoping that enough will make it to the market to make this talk somewhat interesting and maybe a little bit of a taste of things to come. So I'm going to start with airborne gravity. I mean, this is really the simplest of all the technologies, well, simplest in terms of understanding the data, but really fairly complicated when it comes to the instrumentation. Now, we've been flying as a community airborne scalar gravity surveys since about 1958. And we've been, in the early days, there were some very long averaging filters we were flying quite high. And nothing changed until about the late 80s and 90s with the introduction of GPS, where we could use differential GPS to measure the aircraft acceleration. And then we've only seen sort of marginal improvements since about the early 2000s. Now, there are many groups working on fancy new sensors like quantum gravity, spinouts like Nomad Atomics and Q Control, and there are actually about 16 of these groups around the world working on scalar gravity quantum sensors, and of course probably a number still working on the old inertial sensors. Now, the issue with is that the performance limitation in an airborne sense isn't the sensor itself. I mean, we're subject to the equivalence principle. This is sort of what Einstein said, and I'm sure you're all familiar with it many years ago, saying that when you're in that aeroplane, you cannot distinguish between gravity and the aircraft accelerations. And for us, particularly since the early 90s, GPS or GNSS has been the go-to method for independently measuring aircraft acceleration and then subtracting that from what the inertial sensor measures and therefore deriving gravity. The only problem is of course, GNSS has an accuracy of around about 0.4 milligauss when we integrate over 100 seconds. So that really has set some hard limits on what can be achieved from a sensitivity and wavelength perspective. And now I know that some groups, and notably Transparent Earth in Perth, has been looking at using Doppler LiDAR as an independent measure of the aircraft's acceleration. However, these Doppler LiDARs are very expensive, and I think there probably only two exists, and the one they used was on loan from NASA. But it does sort of give you a little bit of an idea of sort of where this potentially could go. If we could measure that aircraft acceleration in a different way, then we could definitely improve that resolution and sensitivity of airborne gravity. Now, I know that some work since last year has been done, particularly by David Becker I think he's at Darmstadt now, but in actually not just using Doppler LiDAR as a replacement for GNSS, but actually integrating it into the same common filter. And I believe there's been some reasonably good improvements in the gravity anomalies that you can now do by integrating it. But I'm not sure we'll see that soon. These Doppler LiDARs are extremely expensive, and that may drive the price out of what's realistic for airborne scalogrammetry. Now, if we move on to gravity gradiometers, I mean, all operational gravity gradiometers right now that exist are based on the original Lockheed Martin's GGI design. Now, the basis of the GGI design was a set of 4 accelerometers that are equispaced on a circle, and with their sensitive axis tangential to the circle and insensitive to the acceleration environment perpendicular to the disk. And of course, rotating this complement moves the gradient signal out to twice the rotation frequency. I mean, this is a clever little trick
So usually when you're dealing with sensors, their performance around DC, drift and so on is the limitation. So by spinning them in this way, you can get rid of all of the problems associated with drift and bias and so on at DC kind of frequencies. So that was really the clever part of that design. But of course, there are limitations to this design. And we have been developing with Lockheed Martin now, probably going on for 10 years, a different approach to the next generation of gravity gradiometers. And where we can measure the tensor, so the gravity tensor, at a single point rather than at multiple points, which is really a consequence of this rotating disk approach. And I mean, it really is a next step in what we'll be able to do with gravity gradiometry. And I think I have a simulation slide which may make visualizing this a little bit easier. So this is just a simple forward model. You can see the model is at the top, and then in this model there are little void locations. These are much smaller, subtler features, the kind of thing that we'd want to be able to resolve with this new gradiometer. So you can see here those are where the void locations are. This is the theoretical response, so GDD, so with the vertical tensor component, and you can see this is what we would. This is, just bear in mind, this is a forward model. This is what we would see with a heli falcon. So really flying as slowly as we can now, with the best instrument we can now, we get this kind of image sitting on the third one over here. And then this is what we expect with Condor. So fairly significantly better. You can start resolving these voids, and that's really the objective here is to improve the resolution and spatial resolution and the sensitivity of the instrument to be, give you the same kind of data that you'd expect from current airborne magnetic surveys. So that's really our ultimate game here. Now, what's next in airborne gear? So, I mean, there's an ongoing interest from the clients, at least the clients we speak to operate at base frequencies lower than 6.25 hertz. Now, maybe that's a kind of a perspective we have, given where we operate, but the issue for us in our EM systems is that the current limitation at lower frequencies is the noise from the rotation of these receiver coils in the Earth's magnetic field. And we've been, over the years, we've devised various strategies to try and isolate this rotational motion from, from what we receive. And so I think we've got a pretty good handle on that. And our rotation isolation systems are pretty good at even very low frequencies at, in the 1 to 2 hertz range. But coils do become significantly less sensitive at lower frequencies, and particularly for our fixed wing systems, we do have space constraints. And what we're working on, and I'm fairly certain some of our competitors are working on, is we'll see the introduction of optical magnetometers in the next 5 years that have sensitivities around what we require, which is about 50 femtoteslas per hertz, but they're going to have limited bandwidth. We can make these optical magnetometers completely non-conductive, so with no metal components whatsoever. But having a bandwidth of sort of almost DC to 100, 200 hertz is not really going to be cut it. So I think we're going to see this fusion of magnetometers and induction coils. And even if those magnetometers at the low end can only measure the total field, I think that's also going to be an option and something that will be looked at quite seriously. And of course, the coil set that you fuse this with will be able to be vectors, result in us being able to measure the vector components. But this fusion of magnetometers
coils. I mean, whether we linearize the coils or not is a different issue, but is almost certainly going to be the next step in the receiver technology. Magnetometers, that's, quantum magnetometers with both the sensitivities and the bandwidth, that we like a DC to say 100 kilohertz is probably unlikely in the next, 5 years or so. Now, moving on to multi-sensor platforms. And I mean, this is something, I'm sure if you're an explorer, it's always been attractive. And there have been many attempts at doing this in the past. Certainly, Excalibur and its predecessor companies have tried these sort of flying laboratories, and all of them have been, even if they were technically partially successful, they've been commercial flops. And that's because there's just too many trade-offs required. I mean, there are combinations of sensors that do make sense, like you can fly a gravity sensor perhaps with EM, and make that work. You can do low-level LiDAR, so wide-angle LiDAR with magnetics. But there are other things that just don't work together. And because of that, this compromise, you fly something, you fly a gravity survey differently to a magnetic survey. And that's sort of part of the reason this has been, not really a commercial success. But I think we will increasingly see some combinations of sensors that do make sense. Like I mentioned a few, low altitude or flash LiDAR together with, say, magnetics or EM. But it's, it's sort of a generic platform that records everything, that records EM, mag, radiometrics, and gravity gradients, and all together, very, very unlikely. And really, it's going to be not just a technical limitation, although that plays a part. It's almost certainly going to be an economic consideration. So yeah, airborne laboratories may look like good ideas, but very unlikely that we're going to see much of them in the future. Now on to some data processing. I mean, we're all making constant improvements in the way we process data. But I think there are going to be some far-reaching changes on the horizon, especially, I mean, whether we like it or not, we're going to have to embrace some aspects of machine learning in our workflows. And one of these, and I'm showing just a particular example here, is how we deal with grading. Now, rather than creating a single continuous map from each geophysical data set, we can use stochastic simulation techniques to generate sort of many possible continuous maps of the geophysical data that all honor the underlying spatial variability. And each map would represent reality. In other words, if we manage to measure every single location in a continuous way, each one of those, these stochastic models could possibly represent the reality. So none of them have a monopoly on the truth. And picking one of them, well, that's a different story. But we can use this ensemble of maps. So we've got all of this large number of possible things that could represent reality. And you can see, sorry, I'm just showing this. Probably not sure the animation is working, but you can see that sort of just cycling between the sort of the possible representations of reality. And but what this really helps us do is it allows us to also compute a quality measure, so an uncertainty prediction that properly accounts for uncertainty in the input. And of course, even better is these kind of stochastic, this sort of large number of simulations really has some advantages when we use machine learning. So I think this approach, it's certainly something we are actively working on, and will probably be launching soon. And I'm fairly certain there will be, there will be either people who will follow or are working on their own equivalent. And this is just another use of the stochastic simulation. And this is
when we do things at regional scale. So this example is from the Pilbara in Western Australia, where MAG survey was conducted at 400 meters. Now, just like super resolution, I'm sure some of you are familiar with super resolution as applied to satellite remote sensing imagery. It's sort of a very similar approach. So we can simulate this data set at 50 meters. Now, typically, we wouldn't want to use interpolation. This is just, again, one of the stochastic simulations. So you're computing many of these and choosing the right one, of course, is the tricky part. But what we can do is we can generate that interpolation uncertainty map, which is what you see in the bottom left. And now we only have to infill the areas that are marked in red. So, and get a product that's probably not that dissimilar to the flying the whole survey at 50 meters. And, but of course, at a much lower cost. And now, I mean, there's no monopoly on the truth here. It'll always be better to fly it at 50 meters, but very often decisions are made that are based on economic constraints. And this is one mechanism where we can make this kind of trade-off. And I think that kind of decision, an economic versus technical decision, or trade-off at least, is going to become a little bit more prevalent, particularly when money is tight. Data integration. So, I mean, this is again another technique which we've been working on recently, and it's based on an algorithm called least-squares co-location, and it's like kriging but modified with harmonic functions to really honor the potential field nature of the data. So this doesn't apply to them. It only applies to potential fields like gravity and magnetics. And you can see, and this is about sort of combining data. So if we have ground geophysics and we have airborne geophysics, or an airborne geophysics data set required by a helicopter or fixed wing, how do we integrate this? And particularly, how do we do this over large regional areas? And then, of course, render this at any level. And this LSC technique works very well. Since the talk, we've actually been using it very actively. However, you can't run it on your laptop. It does need a decent sized cluster to be able to do this. Solving some of these squares problems is a big issue. It requires big matrices and lots of compute power and storage space, but it does provide a combined image or combined grid which also comes with the quality measure. So, and that's really where this technique works very well. So, I mean, right now we're flying a big survey in Zambia. We have some historical data from the government, and of course we have the data we're collecting now. And fusing this into a single data set, and then still having a quality measure, sort of kind of where this is going. So again, if we want to do machine learning, we don't really want to do this on individual little postage times data sets. It's much easier to deal with this at regional level. So this LSC, or least-squares co-location technique, is really powerful when it comes to this kind of integration. And that's just an example. This was the two data sets, one collected with a helicopter, one collected with a fixed wing. And you can see we can render it at various altitudes. And it's really the noise covariance matrix in the LSC equations that stabilizes this. Well, it's not really continuation, but we call it continuation, but it's around that covariance matrix. So we don't have to play any other fancy tricks, and it does provide a nice consistent approach. I'm going to run out of time, so I'm going to speed up a little bit. Machine learning, I mean, I was a bit of a skeptic, but I think there are some really powerful areas where this makes sense. And one of them is MAG compensation. I mean, the way we've been doing MAG compensation in airborne environment,
is the same as what was introduced in the probably the early 90s, which is a physical model with which sort of we explain it in terms of well, it's the induced field in the aircraft skin plus the eddy currents plus some derivative of that, and that's what we're correcting for. Now that ends up with a very simple linear model of about 27 terms, and we can use retrogression to stabilize that inversion of that matrix, and then calculate these coefficients, which will apply to correct the data. But it doesn't take into account a whole lot of other things like moving ailerons and other currents flowing, in cables in our aircraft, and taking a neural network kind of approach with this makes a lot of sense. So we can, this is just a calculation here, just saying that when we deal with just 27 neurons in a hidden layer, it works just as well as retrogression. But we can introduce other things. We can introduce measures of these currents. We can introduce, when we collect gravity, we can introduce all the IMU measurements. They're very precise and they really make a big difference. So that's what the machine learning allows us to do. Add all of these other measurements to improve that compensation. And I think that's a very valid use of machine learning, and has some very simple benefits. Now, there are others. I mean, we have a number where being able to do QA/QC has shown potential, and there are a number of other potential benefits. Now, quantum computing. I'm not going to spend a lot of time on this, but really our interest would be in doing 3D geophysical inverse problems. And the problem with that, of course, in quantum computing is we will require as many qubits as there are elements in the model. And I think most of you know that quantum hardware is currently restricted to a few thousand physical qubits, and they have very, very good decoherence times. And we'll need to wait until we reach the tens of thousands of qubits that are resistant to noise, and we'll be able to construct a network of sort of logical qubits that are large enough to start executing really useful algorithms. Look, I can continue talking about this, but I'm not sure that we're going to see a real practical application of quantum computing in geophysics anytime soon. We're not even sure if quantum computers can solve these NP-hard problems that sort of come up fairly often in geophysical inversions. And certainly quantum computing won't be the panacea for all of these hard problems. And a poorly defined inverse problem will remain a poorly defined inverse problem. So I think we'll see some researchers playing with, how do we state these sort of classical computational problems as quantum ones. But I think we're going to have to wait some time before we see some real progress there. Continuing with that machine learning theme, I think most of what we've been doing with machine learning is largely restricted to 2D. Things like prospectivity maps, sure, AI works fine with that kind of thing. And we've also seen the construction of these sort of very high-dimensional data cubes. And there's some good examples of companies that have commercialized those, which comprise these hundreds of layers of physical, geochemical, and imagery, and so on, and where algorithms are trained and applied. But they're really applied as sort of in a 2D sense. Doing this in 3D is a whole lot more complicated, and certainly level set methods to better define relationships between geological units is an area where there's sort of active work being done. Using Gaussian process is another area which is seeing some good progress. But I think for now, for the next few years at least, AI-assisted interpretation is going to become more prevalent, and of course there is going to be some movement towards figuring out how machine learning can be used to define these geological relationships in 3 dimensions. But that's maybe a little step too far, and certainly not over the next few years. Other applications, we're seeing this more and more in the market.
for geophysical data. GPS denied navigation, of course, bigger deal now with the war in Europe, in the Ukraine, and it looks like magnetics is going to be the go-to solution for what's called PNT resilience or GPS denied navigation. And this is where GNSS gets spoofed. And of course, it's very hard to jam this magnetic field and mess with it. And there's a lot of effort going into this. This, I think, I went to a conference not too long ago where they said between now and 2030, this is a $6 billion industry. So completely dwarfs anything that we do in geophysics. But very much looks like it's going to be around this magnetic field. Geoid surveys, I don't need to, I think most of you have been exposed to this. This is about improving the quality of the vertical measurement we get with GNSS. And it's based on a model, and that model is called the geoid, and the geoid is derived and using airborne gravity and satellite gravity and ground gravity and anything else gravity. But most of the world still, the vertical datum is not well defined, and there's a drive to get this down to a few centimeters, and airborne gravity is certainly playing a very key role in that. Now, I'll skip this slide. I didn't have this in my presentation last year, but I was asked, and that's not really strictly geophysics, but we are looking at developing other airborne instruments. And one of these is a Raman airborne laser Raman spectrometer, which we initially targeted at measuring hydrogen at the surface. So fly around with a big Raman laser, that we can get Raman scattering from gas, and we can measure the gas concentration in small increments from the aircraft down to the surface. So it's time resolved, a LiDAR system, so we can measure that sort of incrementally down. And of course, we wanted to do that because with natural hydrogen, the concentration at the surface is something we can measure. And then at about 30 meters above the ground, any hydrogen that escapes from sort of, when we used the example in Mali, the flow rates from that as an example, at 30 meters, it's indistinguishable from the background. So we really had to come up with a technique that could measure hydrogen at the surface. And the only way we know how to do this is using Raman spectrometry. And so last year, we had just finished our proof of concept prototype, so doing it in the lab. We've subsequently now scaled that up, and we've acquired an optical lab, and buying the bigger lasers and so on that we require to get an airborne prototype up and running. And of course, it also turns out that there are other target gases, so we're not only limited to hydrogen. And some of these other gases like ethane, methane, and CO2, and ammonia, and so on, have much bigger Raman signatures. So it's certainly expanding, and it's looking very promising. And we've done tests now up to 10 meters, which is currently was our initial lab, was sort of the longest distance we could measure. With a new lab, we can go to about 60 meters, which is kind of where we want to be to get an airborne prototype up and running by next year. Yeah, that's sort of the trials at 10 meters. This was done a few months ago, and you can see, it's working kind of the way we want to. We do use single photon counters, so you can see the low count rates, but it scales. So bigger lasers, bigger telescopes to collect these photons really works as well. I'm just mentioning this. I know this isn't geophysics, but it's sort of it's pretty reliable. And increasingly, as we look at this, it sort of kind of looks like hyperspectral data too. So we can use all of the same techniques we typically use with hyperspectral data. So I think that's it. I